Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over entropy and changes of state. So let's talk about the concept for a little bit. In my next video I'll talk about how to calculate entropy for changes of state. So again, we'll talk about what we mean by entropy. So informally, again, what we mean is that to use an analogy, we're talking about the macroscopic disorder of things. So we're talking about going from a gas or going from a liquid to a gas or from a solid to a liquid or from a solid to a gas. We're talking about the increase in just disorder of the molecules. So molecules and the particles are more disordered when you melt them from, say, go from a solid to a liquid, or if you evaporate a substance, you're going to the particles of a gas. And so the gas particles are going to be more disordered than that of the liquid, and the liquid is going to be more disordered. The particles of liquid are going to be more disordered than that of a gas. But in a more formal way, we want to identify or define entropy as being related to the number of energetically equivalent ways of arranging the particles, right? That was that W in the equation, right? So if you write the equation down again up here, so S is entropy is equal to Boltzmann's constant multiplied by the natural log of W. W is that number of energetically equivalent ways of arranging particles, right? Those microstates. So when we're talking about differences in energy, it's going to be related to that number of energetically ways of arranging particles in each of those states. So if we're looking at gas, liquid, and solid, gases have more microstates or more numbers of energetically equivalent ways of arranging particles compared to that of a liquid, and then liquids have more microstates or ways of uh, arranging your particles in energetically equivalent ways compared to that of a solid. So if we think of gas, so if we gas and solid, so gases have more ways to distribute its energy than a solid. So again, bringing in that idea of a dispersal of energy, there's dispersing or distributing the energy of the substance. So in a solid, it's really stuck in place. You really can't distribute the energy very much. But in a gas, that the gas particles can go out and disperse and bring along with those particles the energy. So another way you can think about this is where is that energy contained, or where is that energy in the solid? So in a solid, the energy consists largely of vibrational energy. So really, the particles are so stuck in their position that they can't really move except for vibrations, and that's where a large majority of the energy is located in the molecules in that substance. So they're vibrating, and so you have this vibrational energy. But then for a gas, because the gas particles are able to move away from each other, they're able to move in different ways. For example, they can move from place to place, straight line motion from point A to point B, right? So that is called translational energy, or translational motion is that locomotion from moving from place to place. So that has translational energy. And then you got this rotational, they can rotate as well. So if you're stuck in a solid, you can't really rotate, but if you loosen up, or if you start putting more energy into the particles and they are able to break free from their attractive forces, right? And so now they can move more easily, and some of that energy is going to go into the rotational motion. So you have translational motion, now you have rotational motion, and so you have those places in which you can put energy. So there are more quote unquote places to put energy in a liquid and a gas compared to that of a solid. and therefore you have more possible microstates. Remember, microstates are those ways of arranging the particles. And so, again, bringing in this dispersal of energy, the more you can disperse, the more possible states you have. Those states are going to be related to places of where you can put that energy, and therefore you have more entropy. And so we can now use that to kind of predict what the sign in the change of entropy will be for states of change. So, for example, so in general, entropy is going to increase, going to be the change in entropy is going to be greater than zero for these following changes in state. So you go from a solid to a liquid, that's going to be an increase in entropy. So entropy is going to be greater than zero. If you go from solid to gas, again, that's going to be an increase in entropy. The change in entropy is going to be positive. It's going to be positive for solid gas. And again, going from liquid to gas is going to be positive, an increase in entropy. And also, if you have a chemical reaction that involves gases, if the chemical reaction increases the number of moles of the gas going from reactants to products, right? If you have more moles of a gas in your products than you do in the reactants, then that also is going to have a positive change in entropy. So more gas molecules means more dispersal of energy, more microstates, more ways of arranging your particles in energetically equivalent ways. So this is kind of more of a conceptual way of understanding how entropy is related to the changes of state. I hope you enjoyed this video. If you learned something from this video, if this video was helpful in any way, please make sure you like the video, share the video, subscribe to my channel, hit that notification bell right up there, and so that way you can be notified by other videos I put out. Also, put a comment down in the comment section. Let me know what you think. Ask me questions. I love questions. And thanks for joining me. Have a great day.